A student came to me a few days ago and said, "I have this wonderful theorem, Mr. Ganson is going to make me lots of money and all these great things, and I'm going to be rich and famous." So I didn't think a lot of it until he actually explained it to me. He said, "What if we have two numbers that are 2 apart?" And let's talk specifically about integers. We have two numbers that are 2 apart, such as 7 and 9. When we multiply 7 and 9, they're going to be equal to the number between them, which in this case is 8, squared minus 1. Well, let's take a look at this. 7 times 9 is 63. 8 squared is 64. Minus 1 is 63. Huh. That's interesting. Now let's see if what other cases this may work for. Let's try, let's say 10 and 8. So if this theory is right, that 10 times 8 should be 9 squared minus 1. Well, 10 times 8 is 80. And 9 squared is 81, minus 1 is also 80. So this is interesting, and that this works for positive integers. Well, the next thing I'm asking, well, does it work for negative integers? And so the next case that he tried immediately, and I'm glad that he attempted this, said, well, if I have negative 1 times 1, that's going to be equal to 0 squared minus 1. Well, negative 1 times 1 is negative 1. And 0 squared minus 1 is also negative 1. And just for good measure, let's see how this works with negative integers as well. We'll take negative 7 and negative 5. Multiple, oops, that's not a 5 at all, that's 7. Take negative 7 times negative 5. Well, so if our theory is correct, this is going to be negative 6 squared minus 1. So negative 7 times negative 5 is 35 equals negative 6 squared, which is 36, minus 1 is 35. So in the cases that we've tried, it seems correct, but as all mathematicians know, these examples aren't all cases, so let's actually do a formal proof for it. And I'm going to call this the Stutzman theorem, tentatively, in honor of the students who brought this to my attention. So the Stutzman theorem. Let's let A, B, and C be integers such that A is equal to C minus 2, which just tells us that these two integers are 2 apart from each other, and that B is equal to C minus 1. C minus 1 being the number between, B being the number between A and C, and we can represent it as C minus 1. So, so the thing we're trying to prove, though, what we're asserting is that A times C is equal to B squared minus 1. On the left-hand side, I'm only going to do one thing to change this. So for A, I'm going to substitute C minus 2, which we had when we began here. A is equal to C minus 2 times C. And on the right-hand side, B squared minus 1, what I recognize is that this is the difference of 2 squares, which will actually come into play later. But specifically, this is going to factor to B minus 1 times B plus 1. Okay. So C minus, so we have on the left-hand side, C minus 2 times C equals B plus 1, sorry, B minus 1 times B plus 1, B minus 1 times B plus 1. Left-hand side, as I said, is going to stay exactly the way that we have it. So this is going to be C minus 2 times C. Now on the right-hand side, we actually have an expression for B. B is, as we see over here, C minus 1. So I'm going to substitute C minus 1 in for B. Now I know I should be a little bit more careful with my parentheses, but because these are B is positive, I don't have to be as cautious. So C minus 1 minus 1 and C minus 1 plus 1. All right, so let's simplify this, the right-hand side. Left-hand side, again, is going to be C minus 2 times C equals, well, C minus 1 is C minus 2, and C minus 1 plus 1 is just C. Q, E, D, I've proven that I've proven the Stutzman theorem that if we have integers that are two apart from each other, that when we multiply them, their product is the difference of the number between them squared and 1. Interesting. So this is the Stutzman theorem. Now, from here I thought, okay, well, this is interesting, but does it work for decimals? I mean, if we have something like, say, 2.4 and 2.6, would something like this work? Well, clearly it wouldn't work because they're not one incomplete number of parts. So I thought of a couple other examples. What if we had, so we started with 7 times 9 equals 8 squared minus 1. Well, what if they weren't one apart? What if instead they were two apart? So what if we had, say, 6 times 10? Or, in this case, sorry, 4 apart. I'm explaining myself poorly. How does 6 times 10 relate to the number between them, which is 8 squared? Well, so this is going to be 8 squared minus something. Well, 6 times 10 is 60. 8 squared is 64. So what number makes these equal? Well, it's going to be, I'm going to use a different color for this. It's 4. Okay. Let's try another example. Let's do let's keep with 8 being in the middle here, and let's do 5 times 11 is going to be equal to 8 squared minus what? Well, 5 times 11 is 55. 8 squared is 64. So 64 minus what is equal to 55? Well, it turns out that that is 9. And any good mathematician should recognize a pattern happening here. Specifically that, let's use green for this, that the thing that we're subtracting here is 1 squared, 4 here is 2 squared, and 9 is 3 squared, which I find interesting because 8 is 3 away from both 11 and 5, 8 for this last case we did, and 8 is 2 away from 6 and 10 in this case we tried here. And that makes sense. If we apply, again, the difference of 2 squares in this last scenario here, 5 times 11 is equal to, we're saying, 8 squared minus 3 squared. Well, this makes sense because 5 is really 8 minus 3, and 11 is really 8 plus 3. And if we use the difference of 2 squares here, well, this factors to 8 minus 3 times 8 plus 3. So I find that very interesting property. So, and this is nice that it's working for integers, and my theory is that this works for all real numbers. Let's do a proof of this, what I'm going to call the Ganson theorem, tentatively, or mathematicians make things way more complicated than they need to be theorem. So we have, let's let A, B, and C be elements of the real numbers. And the only condition we're going to put on this is that B is between A and C. B is exactly in the middle of A and C. Well, the way we're going to do this is we're going to say that B is the average of A and C, or A plus C divided by 2. And the theorem I'm asserting is that A times C is equal to B squared minus the distance between B and either of these numbers, which we'll represent as C minus B. I could have used A minus B, but we'll use C minus B squared. So this is the Ganson theorem that I am asserting here. And the thing I really like about this is I'm going to leave the left-hand side completely alone. I'm only going to deal with the right-hand side of this. So on the right-hand side, I'm going to make the right-hand side look like the left-hand side. I have B squared minus C minus B squared. Now there are a number of ways we could go about this. We could FOIL this out. We could we could substitute A plus C over 2 for B. But and we actually will do that later. But I'm going to deal with the difference of 2 squares again. I'm going to write this as B minus C minus B. and I do need to be very careful with parentheses here, times b plus c minus b. Let's do a little bit of simplifying here. B minus c minus b, I have to distribute this negative to both of these terms. So b minus a negative b now gives us 2 b's minus c. And over here, I have b plus c minus b. Well, b minus b is nothing, and so we're just left with c. At this point, I'm going to substitute for my b here. I'm going to substitute what I began with, this initial assertion that a plus c over 2 is equal to b. So instead of b, I'm going to have 2 times a plus c all over 2 minus c times c. Well, what's going to happen here, and I'm going to scroll down just a little bit so we have a little bit more room to write. What's going to happen here is my 2's are going to cancel, so I'm left with a plus c minus c times c. And as we see here, that my c's are going to eliminate, so I'm left with a times c, which is equal to the left-hand side. So the thought here is, and the reason I call this the mathematicians make things way more difficult than they need to be. Here we're just taking the basic concept of two real numbers multiplied by each other, and equals this weird difference of two squares thing. And my thought is, this is very interesting. I like playing with numbers. It's a very fun idea, but I don't know if there's any practical purpose for it. So the question that I throw out here is this something interesting? Has this been done before? Is this a thought worth publishing, possibly? So if you have any thoughts or comments on that, please let me know. Thanks a lot for listening.